Okay, so here is example 17.5, and we want to select drive components for a 2-to-1 reduction, 90 horsepower input at 300 RPM, moderate shock, an abnormally long 18-hour day, poor lubrication, cold temperatures, dirty surroundings, short drive, which means the center to pitch ratio is 25. Okay. I don't know if they ever actually address in this the poor lubrication, cold temperatures, or dirty surroundings. It's a little weird. And the exceptionally long day was sort of a weird statement. I think they were trying to be funny. That's what I think. So let's look at this in the show and discard these things and come and take a look at our example. And I don't know why that thing is moved like that. I guess I'm just having one of them days. Okay, so we had 2-to-1 reduction. So some choices that we will make from this, they didn't tell us how many. Well, the typical one is the sprockets are on the smaller one are 17 teeth. So let's choose that. That means that the other one is going to have 34 teeth. 17 times 2 is 34. It is. And we're going to have our nominal horsepower is going to be 90. Right? And our RPM, and this is going to be the RPM of our smaller sprocket, is going to be 300 RPM. All right, so, and we also, we were told that C over P was 25, which we'll see how we use later on. So one of the choices that we're going to make as part of this, according to the example, is we're going to have a design factor of 1.5, right? So this is something we are going to choose. Something we could go back and maybe revisit if we end up getting something that we think is overly large. We're also going to have a moderate shock, so we choose this, right? So we see moderate shock, and our decision is to use this. Now, I don't think we see in Shigley a section in the chain section which gives us that that moderate shock thing. But we could go back and look at other places where we had something. So there is one under, I think it is near, here we go. For V-belts, right? They have a service factor for V-belts, and this should look a little bit familiar to you, right? That we have the driven machinery is uniform, light shock, heavy shock, that type of thing. Source of the power, normal torque here are high or non-uniform torque. So you can kind of see that we have this sort of judgment call range that we can make. So let me jump back over to if you'll recall the stuff when we had or here, remember the gears, remember gears, where we had this overload factor, we had uniform and light shock, that type of thing. We're making a judgment call. We can use that other information. We don't want to misuse it, but if we need to make some type of judgment call, that's the thing that we would base it on. Right, so in the example here, they chose to use 1.3. Right. Okay, and so let's see. What we're first going to start out with is take a look at the equation. Okay, because there's 17 teeth. We're going to see later on when we have this maximal allowable power. We'll see the equation K1, K2, H tab, right? So this is the tab. This is going to be the tabulated, or I accidentally hit that. So one note's going to wake up. I'll close you up again. So that's this equation right here, right, where the H tab is the tabulated one. That's the power that we get out from the manufacturer right there. And K1 is based on the number of teeth other than 17. So we have 17. So K1 is going to be equal to 1. So I wrote that down. K2 is going to be a strand correction. So if you have more than one strand, and we don't know that yet, we don't know how many strands, we probably want to choose a different strand, right? So our K2 is to be determined right in there. But we do see that our HD right here, we want to set this whole thing equal to HD. Let me see what the horsepower that must be transmitted is HD, right? Which they're saying is going to be the nominal. I'm going to keep writing the thing down wrong. Let me close them down here. So the H nominal times that factor, the service factor, times the safety factor, right? And we chose that safety factor. And there was an engineering judgment that was taking place when we chose these two things from right up here, right? So what we're going to say here first is if you want to find the H tab, because we're going to look for that, we're going to take the H nominal right here times our KS and our ND, and we're going to divide it by K1 and K2, right? So we took 90, multiplied it by 1.3 and 1.5, and we took K1 is going to be equal to, let's see, I said that was K1 is equal to 1 for 17 teeth. So that's 1. We don't know how many strands yet. So what we can do is we can calculate that as 176 over K2. And so if we were to find this, let's set up a little chart onto the thing. I'm not going to do it the same way that they did it in the book exactly. But let's say that we have strands, right? So we have number of strands, 1, 2, 3, 4, and we might need more than that, but we're only going to go down. So the K2 that we're going to look that up, that's going to be from this right here, right? So we will say, I'll write down right next to it, we have 1, 1.7, 2.5, and 3.3, etc. What we can find then is the H tab, right? We're just going to plug those numbers in for right here. So we'd say we have 176, we have 104, 70.4, and 53.3, right? And so now if we go up and let's check out, so let's see, I think I can put this up next to the thing. Let's close this down here. Can we close that? I can't remember. Can I? How do I close that tab thing over? I think I just closed it there. There you go. So let's take a look at our chains. Okay. So what we're doing is we're looking for powers in here that will, and we're going to 300 RPM. We got to remember that, right? So we're going to look through this list right here. We could also have looked through this list right here, but we could see that our powers aren't even close to being in our range, right? So we're going to find what chain number to use for 176. We could see that we could do it with 200, right? So we'll do 200 is the chain number. For 104, we'll see that 160 can do it. And for 70.4, it looks like 140 can do it. and for right here for 53, it looks like 140. So it looks like 140 is a pretty good candidate. Something a little weird in the book here. You'll notice that this, we want to take a look at the type, right? So this guy, right up here, this is weird. I said 170. Yeah, okay. So you'll notice that this is type C prime right there, which you'll see down below. Says that this thing is actually in the galling region. So we probably don't want to pick this one. The next one we found was like 160, and it was just sort of on the borderline of this type C and type B lubrication, right? So we probably want to prefer if we could do the oil bath instead. So I think the decision is to go with the 140 right here, and we notice that's going to be 3 strands. Maybe we go with 3 strands is going to be enough. So that's some of the decision. We'll have M is equal to 3 strands. I think they decided to go M. Yeah, 3 strands. The chain number is 140 right there, with the tabulated horsepower of 72.4 right there. Horsepower, right? Okay. And so coming back onto here, so if that's true, what we also find, let me come back, we want to find from table 17.9 or 1720. Why did I say 17? 1719. From that, we can get we picked 140, right? So we can find out that our pitch is going to be equal to 1.75 inches, which seems like that's going to be a pretty big chain, isn't it? We're talking a big honking chain there. And they give us some other dimensions. They do give us the tensile strength. I don't think we're being asked to use that right there. Give us the weight and so other dimensions that we might have wanted to have right here. Now we also want to get so part of the problem probably wanted to also figure out what the configuration is, what the dimensions are going to be. So as part of that, we wanted the center to center distance is kind of an important one for us. So we come through and we could use this equation right here, center to center distance, which means that we have to use this thing A to be put back in there. I guess they just maybe tried to make this a shorter equation. So I can write down this. First off, I need A, right? Actually, I need to be able to do this. I need this L over P, right? So I need the length per pitch, and they're saying that we give the approximate chain length from here, and then once we have that L over P, we can use A, and then we can find the center to center distance, right? So we start out with L over P, and they used approximately, and they say it's going to be 2 times our C over P. Well, our C over P we were told was 25, right? So that's like a decision maybe that we're going to kind of make, something that we know from experience apparently. And then we're going to have N1 plus N2 over 2, right? So we're going to have 17 plus 34 over 2. And then for, let's see, we're going to use plus N17. No, we're going to have 34 minus 17. Squared divided by 4 pi squared, and then c over p, which was 25. And I sure would like to do the I'd kind of like to try this out right here, to try to figure out what these how these geometries worked out. I need to try that out, to try to figure that out sometime. Haven't got around yet. So anyway, we find 75.79. That's length per pitch right there. So let's use an integer of 76. I just wrote down 17. Of course, you can't see what I just wrote down. That's good. I'll pretend I didn't write it down. 17 lengths that we should use. So now, coming back over here to this equation A, we can find n1 plus n2 over 2 minus L over P right there, which we found to be right here. So, okay, we have, once again, 17 plus 34 over 2 minus, that's not good. I think we're going to get a negative number here. Yeah, I guess that's supposed to be, though. We get a negative 50.5. And then we can put it into this equation to figure out the actual center-to-center distance onto the thing. And once again, I kind of wish that I had actually done this, figured out this geometry myself. I don't need to write the equation down. It's right there next to us, right? So I have 1.75 and write this out. Let's see. Where'd you go? I'm losing it. Okay. Minus. I think it's minus. Yeah. I wrote next to mine. Minus 50.5. That's a weird equation. Why did they do that? I don't know. Plus square root of minus 50.5 squared plus the, well, I said plus, but it should be minus 8. This has got to be a geometry thing. 34 minus 17 divided by 2 pi squared, that whole thing. And if you do that, you get 25.1. They said pitch. Wait, is that true? I didn't calculate that. All right, so I guess they didn't put the 1.75 in at this point right here. All right, and then they actually get the center with the 25.10 times the 1.75. So they get the 43.93 inches distance in between. So we have quite a few things decided, right? I think with that pitch, we'd also get what the diameters were, and I'm surprised that we didn't write what those were down. I would think that we would want to know what the diameters are. This operating is on the pre-extreme portion of the power, so durability estimates other than 15,000 are not available. Given the poor operating conditions, life will be much shorter. That's a nice thing to know. But for the diameter, I think it's you're going to use the same type of diameter that you would for that you would expect. Yeah, you go like this. For sprocket teeth right there. I think the D that they're talking about here is the outside diameter. The pitch diameter sprocket, denoting the chain pitch by P, the pitch angle here. Okay. Yeah, no, they're not saying anything revolutionary as part of this right here. They're using this to determine what that angle is going to be. But I do believe that we would find the diameter just by this right here, right? Because this of the sprocket. And I don't know why we don't just write that out somewhere. But, okay. So we would find the diameters. Diameter 1 here would be 17 divided by 1.75, right? So 17 and 1.75. So that seems pretty small, 0.5714. That's itty bitty. I don't trust that. I don't trust that at all. I want to reconfirm that that's how big the diameter should be. Let me try that again. No, I did that wrong. 17, 1.75. Yeah, that should be. Can't do math. So that would be 9.714 inches. And then D2 would just be 2 times that, right? So that would be pretty big, right? So the 19.43. And these are going to be like a nominal pitch diameter, right? So you're going to have like the teeth kind of like that right there. They show that down here, where they show here's the pitch diameter right in there. So we have maybe enough information to try to align what these are going to be. We have the chain type and number of strands. You're going to have 3 strands. They're going to be this far apart. And we have the chain length right here is going to be this, right? So the length is going to be that 76 times 1.75. So the length of the chain, 76, 1.75, is going to be 133 inches long. So we have the diameters, the length, and the center to center distance all there. So that's our chain design. And that is our lengthy video, 22 minutes long.